In this video, we're going to discuss an application in which the polar coordinate system will be helpful. So we use the complex plane, not talking about the polar coordinate system yet, but talking about complex numbers. We use the complex plane to graph numbers of the form z is equal to a plus bi, which is what we call a complex number. So a complex number consists of potentially two parts, a, which we call the real part of the complex number, and b, which is associated with the value I. We call this the imaginary part of this complex number. I is what we refer to as the imaginary unit. So it's worth reviewing the concept behind I. Just as a refresher, what does I actually mean? Well, imagine you were trying to take something like the square root of -4. Suppose you were trying to evaluate that. Now, we all know how to evaluate the square root of 4. That's not a problem. The problem is that this number is negative. So what we're asking when we look for something like the square root of -4 is we're asking what number would we have to multiply by itself in order to get a -4 out? Well, immediately you might say -2. But what happens if you multiply -2 by itself? Well, if you multiply a negative by itself, the two negatives cancel out and make a positive. So positive 2 times positive 2 is positive 4, and then -2 times -2 is also positive 4. So what would you multiply by itself to give you -4? Well, the answer is there is a number that you would multiply by itself to give you -4, but it's not a number that exists within the standard real number system, our standard numbers from -infinity to infinity. So the way we handle this issue is by adding on a new set of numbers, what we refer to as complex numbers. So how do we handle actually evaluating this? Well, again, the 4 is not a problem. The problem is the fact that there's a negative attached to it. So I'm going to use one of the rules for radicals that says that if we have a number multiplied by another number, then we can split that up into two separate radicals. So I'm going to split that -4 up into a 4 and a -1. And again, that product rule for radicals says that I can write that as the product of two separate radicals. So this is helpful because, again, square root of 4, we all know how to evaluate that. That's going to be 2. The square root of -1 is the part that gives us the problem. And this is not something we can evaluate in the context of the real number system, the numbers we typically see. So this particular value, the square root of -1, was relabeled by mathematicians with the value I. I stands for imaginary. This is the imaginary unit. It's that thing that gives us trouble when we try to take a square root. So rather than writing the square root of -1 every time, we just replace it with the value I in order to indicate that we're talking about something related to the square root of a negative number. So this is what we would refer to as a purely imaginary number. It only has something attached to the imaginary unit. A complex number is a little bit more general. Not only do we have something attached to the imaginary unit, but we also potentially have another part that is not associated with the imaginary unit. So again, a real part, A is just a real number, any number we want, standard numbers from -infinity to infinity, and B will be a real number coefficient for the imaginary unit I. So when we graph complex numbers, we actually graph them very similarly to how we graph ordered pairs. So A, what we refer to again as the real part of the complex number, is graphed on what we call the real axis of the plane as a horizontal coordinate. So essentially it graphs the way we normally graph an x coordinate. And then B, not BI, but just B, just the coefficient for the imaginary unit, is graphed on the imaginary axis as a vertical component. In other words, it looks like the y coordinate. Okay, so let's practice graphing some of these. And again, it's basically like graphing an ordered pair. where we have just a different form for how the ordered pair is written, and we have slightly different labeling for our coordinate plane. So it looks basically like an XY coordinate plane, no real difference. The difference is how we label it. So rather than labeling our horizontal axis as the x-axis, we label it as the real axis, sometimes abbreviated RE. And then our vertical axis, we label that as the imaginary axis, sometimes labeled as IM. Okay, and so what if we wanted to graph something like 3 plus 4i? Well, 3 is the real part, which means we would go out to 3 on the real axis. And then 4 is the imaginary part, which means that from that particular location, we go 4 units vertically associated with that imaginary axis. So 3 is the real part, and then 1, 2, 3, 4 is the imaginary part, which takes us to this particular location in the plane. So this is going to be A. What about 4 minus 2i? Well, again, we have a real part. We have an imaginary part. In this case, the imaginary part is negative. So we go out to 4 on the real axis, and then we move negative 2 units vertically, which would take us to this location. So that is going to be the location represented by B. And then we also have special cases. So negative 5 is technically a complex number. It fits within this pattern if we were to allow B to be 0. So if you only have a real part and you allow your imaginary part to be 0, then you generate a real number. So the real number system is actually a subset of the complex number system. Every real number can also be written as a complex number if you just choose a value for B of 0. So how would we graph something like negative 5? Well, it's graphed purely on the real axis. So we go out to negative 5 on the real axis, and again, it's basically like having a y-coordinate of 0. Because there's no imaginary part, we graph strictly on that axis. And so that is going to be the location for C. And then D is what we would refer to as a purely imaginary number. In this case, the value for A, the real part, would be 0, and then the value for B, the imaginary part, would be negative 3. So if the real component is 0, that means we haven't moved horizontally in the plane. It means we've only moved vertically, and we've moved down 1, 2, 3 units. So that is going to be the location for D. So not too challenging, again, basically like graphing ordered pairs, just in a coordinate plane that's been labeled in a different way. Now, in order to talk about complex numbers in the context of the polar system, we need to define a couple of different things. So the absolute value of a complex number, what we also call the complex number's modulus, and you'll hear me call it the modulus of the complex number. What is absolute value normally? Well, absolute value takes a positive number, makes it positive, takes a negative number, makes it positive. But more specifically, an absolute value represents a number's distance from 0. So if we're talking about the absolute value of a complex number, something that graphs in the complex plane, then the absolute value, or the modulus of the complex number, is the number's distance from the origin in the complex plane. So in other words, if you were to start at the center of the plane and then travel directly along the shortest path to your particular complex point, well, how far would you have to go? What's that distance? That is defined as the modulus of that complex number. And we can find this value, the modulus, using a variation of the Pythagorean theorem, which will also look very similar to one of the formulas we used when we were talking about the polar coordinate system. So remember, we had the formula r squared is equal to x squared plus y squared, which allowed us to take rectangular coordinates and find a directed distance. Imagine just taking the square root in this case and just isolating r with a positive square root on the other side. Essentially, you're going to see the same formula here. Now, what has changed though? Where we have x, we're now using an a, And where we have y, we're now using b, because a is our horizontal component and b is our vertical component versus horizontal and vertical given in terms of x and y. So it's really just a different labeling of this same relationship. Now when we talk about absolute value, the notation is vertical bars. So even in the context of this kind of problem, we're still going to use the vertical bars to indicate the absolute value or the modulus. So the distance from 0 for the complex number is going to be the square root of the real part squared plus the imaginary part squared. Now notice I didn't include I. I is the imaginary unit. It's its own thing. When we talk about the actual real and imaginary part, we're just talking about the real numbers, A by itself and B just the coefficient for the imaginary unit. So you're not going to see I involved in a formula like this. We're just looking at those constant values A and B. So whatever this comes out to, this is the distance to go from the origin to any of these values in the coordinate plane. Okay, so let's practice finding the modulus of some complex numbers. And since we have a formula involving a square root, of course we know we may run into some irrational numbers. We can either leave them exact in terms of an irrational number, or of course we can approximate them if that's the goal. So let's find the modulus of each of these complex numbers. So our first one, z is equal to 3 minus 4i. So we want to find its modulus, its absolute value. So I'm going to take the square root of the real part squared plus the imaginary part squared. So that's going to be the square root of 3 squared plus negative 4 squared. And you may recognize 3 and 4 as a Pythagorean triple, which means this is going to work out nicely. So 3 squared is 9, 4 squared is 16, so negative 4 squared is also 16. And so 9 plus 16 is 25. And so we're taking the square root of 25, which is 5. So if we were to graph this particular complex number in the complex plane and take its distance from the origin, it would be exactly 5 units away from the origin. Okay, what about this one? 8 and 2 do not comprise a Pythagorean triple, which means more than likely when we find this particular number's modulus, it's going to be an irrational number. So the modulus of z is equal to the square root of negative 8 squared plus 2 squared. Okay, simplifying that down, negative 8 squared is 64, 2 squared is 4. So that's going to be the square root of 68. Now, if that is as simple as it gets, then we can leave that, but we do need to verify whether or not this can be simplified. So 68 itself, if we were to take the square root of 68, 68 is not a perfect square. Okay, so we cannot evaluate the square root of 68 directly in the calculator. However, if we can find a square root that's a factor of 68, or find rather a perfect square that's a factor of 68, then we can use that to partially simplify this radical. So what sort of things are we looking for? Well, maybe 4 is a factor, maybe 9 is a factor, 16, 25, those kinds of numbers. We want to see, do any of those numbers, those perfect squares, divide into 68? So just try some. Try 4. Start with 4. Well, we luck out. 4 divides in. And notice we're left with 17. 17 is not going to be divisible by anything else, which means 4 is going to be the largest number that divides in that's going to be of use to us. So I'm going to take the square root of 68, split it up into 4 and 17, and then I'm going to use that same rule I used with root negative 4 and essentially apply that rule here. So I can take the square root of 4 separately from the square root of 16, or excuse me, not 16, 17. And the benefit of that is the square root of 4 can be evaluated and simplified. We know the square root of 4 is 2, and then we're just left over with the square root of 17. And so that will be the modulus in this case. In this case, it is an irrational number, which is normal. We do expect to see that from time to time. Well, based on knowing how far a complex number is from the center of the graph, we can define the polar form of a complex number. And so essentially what we did with the polar coordinates, we're doing the same kind of thing here. So in terms of polar coordinates, we had r, we had theta. R was the distance from the pole, the center of the polar plane, to the actual point in question, and theta was the directed direction. So r is directed distance with a direction of theta, which just essentially tells us how far do we have to rotate around in order to get to the particular location in question. So we're going to use this modulus, this value we just found, to convert our complex number from rectangular form to polar form, again in essentially the same way as we did it with basic x and y coordinates. So now we are in the complex plane. So this is not x and y, this is real and imaginary. So if this is our particular point, this is going to be z is equal to a plus b I. It's not an ordered pair, it's a complex number with a real part of a and an imaginary part of b. So this is also going to be a, and this would also be b, if we want to think of this in terms of like a right triangle, right? That looks familiar. So in terms of the polar system, we're representing the same kind of locations, we're just representing them using different coordinates. So remember, we define the direction in terms of how far we rotate from the positive x-axis, or in this case the positive real axis, so this will be theta. And then this particular distance right here, in our normal polar system we called that r. Well here, this is now the modulus of z. So as opposed to calling it r, we just label it with this new labeling based on the context of this particular kind of problem. So based on that, this will be the form for our complex number in polar form. And it's not going to be the same as just writing a point, writing an ordered pair, because we're not talking about ordered pairs here. What we're going to determine is how we write a and b in terms of z and theta, or specifically the absolute value of z and theta. So here is the setup. When we write it in polar form, it's going to look like this. It's going to be r times, in parentheses, the cosine of theta plus I times the sine of theta. So where we normally write just an ordered pair, r and theta, this will be the notation we use when we write our complex number in polar form. And we're not going to evaluate cosine of theta or sine theta. If you see something like cosine of 30 degrees or sine of 30 degrees, of course your instinct is to simplify that. That's not the goal here. The goal is to write this form as is verbatim. So whatever theta is, it's going to be cosine of that value and sine of that value verbatim, not the actual numbers, the trig functions as written. So r times cosine theta, or rather it should be magnitude of z. Let's use magnitude of z. Let's keep it correct. Careful about our notation. The magnitude of z, what we think of like r, is going to be replacing r again, and then the real part here is going to be a times the cosine of theta, or excuse me, a is going to be r, the magnitude, times cosine of theta. B is going to be r, or the magnitude, times the sine of theta. And then r, or rather the modulus for z, is going to be the square root of x squared, or a squared plus b squared. Excuse me, I'm getting all the terminology mixed up. Let's keep things straight. A and b, not x and y. And then to find theta, the tangent of theta is going to be b over a. So really, these are the exact same relationships we saw in terms of converting from polar to rectangular and from rectangular to polar. It's just we have magnitude of z, or excuse me, the modulus of z in place of r, and then we have a and b instead of x and y. But otherwise, it's really all the same relationships. So the value of r is the modulus of z, and again, we've kind of double labeled just to be sure that we know what we're talking about here. Now theta is what we refer to as an argument for z. It is an argument for z. Now we know based on the standard polar system that theta can have a variety of values and still take us to the same location. So any number, any radian measure or degree measure that's coterminal to the particular angle in question will also take us to the same location in space. The same thing is true here. So there's actually going to be a variety of ways to write our complex number in polar form, just based on the idea that theta can have a variety of values and still take you to the same location. If you rotate it all the way back around, added another 360 degrees or 2 pi, it takes you back to the same location. Typically though, we're going to try to stay between 0 and 360, between 0 and 2 pi, depending on which type of measure we're talking about. So normally we want the value of theta that's on the interval from 0 to 2 pi in terms of radians, or 0 degrees to 360 degrees in terms of degrees. So in a lot of situations, what we're going to do next, we'll end up with angles that are outside of those intervals. That means we're going to want to take the extra time to find the coterminal angle that is within the interval of interest. So I would take some time to really study this kind of diagram, and again, it's the same kind of setup we had when we just converted x and y to r and theta, and vice versa. But think about how things change in terms of the new context. Most everything stays the same, but we need to be comfortable with the transitions and notation, because that is ultimately what's changing in any of these situations. Okay, so the next thing we want to practice is just writing our complex number in polar form. This doesn't explain why we want to write them this way, but we'll get to that. So let's just practice writing them in polar form, and then we'll talk about why this matters. Okay, so for each of these complex points, complex numbers, we want to write them in polar form. So in other words, we need to find the modulus, which is like our value for r, and we need to find theta. We need to find the direction that we rotate in. So -2 plus 2i. Now I want to graph this first. We at least need to have a sense of what quadrant this is in. This is going to be important in a moment. So -2 plus 2i. So that is a negative real part and a positive imaginary part, which would take us somewhere like this. Okay, so if we were to look at the distance from the origin, it's going to be that, and then our angle theta will be the angle that rotates us around from the positive real axis to that particular location. So we want to know what is the directed distance and what is the direction. So the modulus of z, which is our distance from the origin, is going to be the square root of -2 squared plus +2 squared. Okay, so that's going to be the square root of 4 plus 4, which is the square root of 8. Now 8 is not a perfect square, but it is divisible by 4, which is a perfect square. So if we split it up into a 4 and a 2, take the square root of 4, which gives us 2, and then we have a 2 left over. So that will be the exact and simplified version of our modulus of z. Now we also need to know the direction angle, and that's going to use the tangent relationship. So we know tangent is defined as y over x. Well here, that's going to be b over a, since they perform the same roles, just in the context of this kind of situation. So the tangent of our angle is going to be -1. Now in order to solve for theta, we have a couple of different options. We could just take the inverse tangent and then go from there. But because its tangent is equal to -1, that's a number we encounter frequently on the unit circle. So we can just determine what theta would have to be based on what we know about the unit circle. Okay, well, we know the angle we want has to be an angle in the second quadrant. So we're looking for an angle, specifically a radian measure, that would be in the second quadrant as rotated from the positive real axis, where the tangent of that angle is also -1. In other words, the x and y are the same, but they differ by a sign. Well, the radian measure where that occurs is going to be 3 pi over 4. So that will be our direction angle. That will be our argument for this particular complex number. And notice it is between 0 and 2 pi, so this will be the version of the argument we want to use. So here's how we're going to write the complex number in polar form. We're going to start with the modulus, so 2 times the square root of 2. And then in parentheses, we want the cosine of our direction angle. And I'm literally just going to write it as cosine of that angle. I'm not going to simplify it. I'm going to write it in this form. Plus I times the sine of my direction angle, 3 pi over 4. So that is my number in complex form. How does this all fit together? Well, this number is factored out. This is a factored form. But imagine if you were to distribute this. Well, if you distributed this, you would have 2 root 2 times the cosine of 3 pi over 4. That looks familiar. That's essentially the structure we had when we looked at the formula for evaluating x when we converted from polar to rectangular. So our modulus times the cosine of our angle represents the horizontal portion, in other words, A. So this is another way of saying A if we were to distribute this. If we distribute it to the second term, we have 2 root 2 times the sine of 3 pi over 4. Well, that again looks kind of similar to what we had as a formula for y in the polar coordinate system. Well, here we're calling that b. We're calling it the vertical component, which is associated with the imaginary unit I. So this is our modulus. This is the distance from the origin. And then 3 pi over 4 rotates around. And this is going to be the form we write in order to do essentially what we're going to do in a moment. So the reason we write it in this kind of strange form is in order to do what we're about to do. We're going to use the complex polar form in order to perform some algebra on complex numbers. So let's try the next one. Not as nice numbers. We'll see what happens. So again, we want to write the polar form of this particular complex number. So let's start by graphing it so we know what to expect. So we have a real part of 8, which is positive, and then an imaginary part of negative 15. So our point would be somewhere down in the 4th quadrant. So we want the distance from the origin, the directed distance, and we also need to know what is the angle that would take us from the positive real axis to this particular location. So it's going to have to be an angle between 3 pi over 2 and 2 pi. Okay, so let's start with the modulus. So the absolute value of z, the modulus of z, is going to be 8 squared plus negative 15 squared. So that's going to be the square root of 64 plus 225. We can put that in the calculator if needed. So the square root of 64 plus 225, well, that comes out to 289, which happens to be a perfect square. We take that square root, so the square root of 289 is equal to 17. So this worked out nicely because 8, 15, and 17 actually represent a Pythagorean triple. So the distance between the origin and this particular location, that's going to be 17 units. Okay, now what about our direction angle? So we know that the tangent of our angle is equal to the imaginary part, the vertical part, so negative 15, divided by the real part, the horizontal part, which is 8. Now, negative 15 over 8 is not a combination that we encounter readily from the unit circle. So the only way to solve for theta in this case is to directly just use the inverse tangent. So that means theta is equal to the inverse tangent of negative 15 over 8. But that's not the whole story. Okay, what do we know about our inverse trig functions? Well, we know that negative tangents, or inverse tangents specifically, is either going to give us an angle in the 1st quadrant or an angle in the 4th quadrant. So if we're evaluating inverse tangent of a positive number, that's going to correspond to an angle in the first quadrant. If we take the inverse tangent of a negative number, that'll correspond to an angle in the fourth quadrant. So this will be a fourth quadrant angle, which is what we want. But again, that's not the whole story. So what happens if we evaluate this particular value? So I'm going to take the inverse tangent of negative 15 over 8. And I'm not worried about whether or not this is in degrees or radians. It's not going to matter. So this is in degrees. So notice we get a negative degree measure. Why is that? Well, the inverse tangent actually gave us that angle, the angle we would get if we rotated backwards into the fourth quadrant from standard position. That's not quite what we want though, because remember, the angle we want is the angle that would be coterminal to this, but is between 0 and 360, or 0 and 2 pi if we're talking about radians. So I need to find the angle that would be coterminal to this one, but would take me into the interval I want. So if I imagine taking this angle and then adding on a full rotation, it will give me the corresponding positive angle that's in the correct interval that meets this relationship I need. So I'm actually going to add on 2 pi radians to that value. And the bad news, unfortunately, is this is the angle. That is the exact version of that angle. Anything else we would do with that would require just approximating something. So if the goal is to find the exact polar form of this complex number, well, this is the exact angle we're going to use. So when we evaluate the polar form, when we write the polar form, this will be the value for theta. So it's going to look really messy when we plug it in, but unfortunately there's no getting around it. So our complex number in polar form is going to take our modulus, which is 17, and then we're going to multiply by the cosine of our angle. Remember, all of this is the angle, all of that is now the argument for cosine. So inverse tangent of negative 15 over 8 plus 2 pi. Okay, it looks awful, I know, there's no shortening it. Plus I times the sine of this same value of our direction angle. So inverse tangent of negative 15 over 8 plus 2 pi. So believe it or not, that is our polar form. So why would we even want to take the time to do something like that, to take something that looks simple and write it like that? Well, again, we'll talk about that in a minute, but essentially there are some algebraic operations that we do on complex numbers that are complicated when they're in the simpler rectangular form. They are very much simplified when we can write these numbers in polar form. So that's going to be the ultimate goal. But before we look at that, let's just talk about converting in the other form. So what if we have rectangular and we want to convert to polar? This is how we handle it. What if we want to go in the other direction? Well, the good news is this is actually very simple, because all we need to do is just evaluate our trig functions. So remember, as I mentioned a moment ago, if we were to distribute our modulus to those two trig functions, then we have r times the cosine of theta, r times the sine of theta. We have modulus of z instead of r, but essentially the same thing. So we have x, we have y, or in this case, a and b. So if we want to know what a and b are, we want to write the standard rectangular form, all we have to do is simplify this the way we normally would. So in other words, evaluate the cosine of 120 degrees, evaluate the sine, and then distribute 4 to both of those terms. So that means z is equal to 4 times, and I'm going to do those trig functions first. So the cosine at 120 degrees is going to be negative 1/2. So negative 1/2 plus I times the sine of 120 degrees, which is root 3 over 2. Okay. So now I can distribute, so that's then going to be 4 times negative 1/2 plus 4 times the square root of 3 over 2 times I, assuming we're writing in the order that we want at the very end. And 4 and those denominators of 2 are going to reduce. So 4 and 2 reduces, leaving us with a 2, so that'll be negative 2. And then 4 and 2 again reduces to leave us with a 2, so plus 2 times the square root of 3 times the imaginary unit I. So conversion in that direction is fairly straightforward, just like it was when we actually did this with just standard r and theta and x and y. Okay, so now let's talk about why this matters. Why do we do these conversions when we take something that looks really simple and ultimately we make it look more complicated? Here's why. So adding, subtracting complex numbers is straightforward in any form. Specifically in rectangular form, it's just a combining like terms kind of thing. So suppose we want to add two complex numbers. Well, we add the real parts. Those are considered like terms. We add the imaginary parts. Those are also considered like terms. And the result is a new complex number. So it's very straightforward, and it looks essentially like what we do with polynomials anytime. We just combine like terms. Multiplication and division in particular are much more complicated from the standpoint of using a complex number. And the reason for that is because a complex number consists of multiple terms. So the fact that we're then multiplying or dividing something that has multiple terms makes the problem more complicated than it otherwise would be if we're just using the numbers we're used to using, just using real numbers. But fortunately, when our complex numbers are in polar form, there are actually simplified ways to perform these operations, to multiply them together, to divide them, and then also to take powers, to exponentiate complex numbers. So we're going to talk about those three operations and what that looks like once we have our complex numbers in polar form. So suppose we have two complex numbers. So z sub 1 is going to be r sub 1, or again, we can think of that like the modulus, times cosine of theta 1 plus I times sine of theta 1. So biggest thing, just make sure you match all of those subscripts. And then z sub 2 defined similarly. So if we want the product of those two complex numbers, it's going to be another complex number in polar form. The modulus is going to be the product of the two original moduli. That's the plural of modulus. So we're going to take the two moduli, we're going to multiply them together, and that's going to be the new modulus. Now what about the argument? What do we do with the theta values? Well, again, we end up with a new complex number, so we're also going to have cosine of theta plus I times sine of theta. But the new angle is actually going to be the sum of the original two angles. So it's going to be cosine of the sum of our original angles plus I times the sine of the sum of our original two angles. And once we evaluate all of that, which really just amounts to multiplying your moduli and adding your arguments, writing it in polar form, then you have the product. And of course, if you wanted to get back to rectangular form at that point, you would just simplify all of that down and do exactly what we did in the preceding example. Now, what if we want to divide? It's essentially going to be corresponding operations. So multiplication results in multiplication and addition. So division results in division of the moduli. And then you can probably guess subtraction of the arguments. So theta 1 minus theta 2 times I, or excuse me, plus I times the sine of theta 1 minus theta 2. Now with division, the order is very important. So with multiplication, you can multiply in either order, you can add in either order, and it doesn't change the outcome. Not the case with either division or subtraction. So the numerator and the denominator for your division must be observed carefully. So it's going to be the first modulus divided by the second, and then the first angle minus the second. The order is going to be important. So let's do a couple of examples using this multiplication and then using this division. So given the two following complex numbers. So we have z1 is equal to 4 times the cosine of 4 pi over 3 plus I times the sine of 4 pi over 3. And z2 is equal to 2 times the cosine of pi over 2 plus I times the sine of pi over 2. We want to find the product of those two complex numbers. So suppose they weren't in polar form to start with. We would have to start by converting them. So these two, fortunately, are already in the form we want, but if they were not, we would convert them first so that we can then apply this formula. Okay, so z1 times z2. We're going to take the product of the moduli. So the first modulus is 4, the second modulus is 2. We're going to multiply those together. And then the angle we use is going to be the sum of the two original angles, which were 4 pi over 3 and pi over 2. And you've probably noticed at this point the angle in each trig function is the same, and that's because the angle is the direction angle. It doesn't change when we use it in another trig function. It's consistent because we're talking about the same angle as associated with that particular complex number and the particular location in which it graphs. So once you find the angle one time, essentially it just means you found it for the whole problem. Okay, so whatever this is, whatever this simplifies down to, it's the product we want. So I'm going to go out to the side and I'm going to do that addition. We need to determine what's that really going to be. So 4 pi over 3 plus pi over 2. Okay, well we know we need a common denominator, so we'll need a common denominator of 6. So that's going to be 8 pi over 6 plus 3 pi over 6. We add the numerators and we get 11 pi over 6. Now, we did mention earlier on that when we define the argument for our complex number, we want to make sure that it's a value between 0 and 2 pi. So whenever we do this addition or potentially subtraction, depending on what operation we're using, we need to make sure that the angle we come up with is one that's between 0 and 2 pi. If it's not, then we're going to find whatever the coterminal angle is that is within that interval. Now, fortunately, 11 pi over 6, it's close, but it's still between 0 and 2 pi. So we can use this as our actual argument. And so all we have to do now is just clean it up. So 4 times 2 is going to be 8. So the modulus of our product is going to be 8. And then our angle, the argument we choose, is 11 pi over 6. So cosine of 11 pi over 6 plus I times the sine of 11 pi over 6. So there we go. That's our final answer. Now, just for the sake of the practice, what if we wanted this in rectangular form? How do you know whether you do? Well, you may be told you want it in rectangular form. Another thing to pay attention to is the notation you're given at the very beginning of the problem. Typically, the notation you're given at the beginning is an indication of the notation that you should use to write your answer. So if you're given a rectangular form to start with, usually that's an indication that you want rectangular form for your final answer. So even though we're given polar form here, suppose we wanted to find the rectangular form. Well, again, all we have to do is evaluate our trig functions, distribute that 8, and then just simplify everything down. So what would this be if we wanted to evaluate all of that? Well, the cosine of 11 pi over 6 is going to be the square root of 3 over 2. And then the sine of 11 pi over 6 is going to be negative 1/2. So I would just distribute my 8 to both of those terms. Now notice the second term is now going to have a negative associated with it. So it's going to turn into a subtraction. So that's going to be 4 times the square root of 3, if I simplify and cancel, minus 8 times negative 1/2 minus 4 times I. So that would be our rectangular form, assuming we wanted the rectangular form. Pay very close attention to directions in terms of notation. If it doesn't say anything about converting back to rectangular form, then your polar answer is fine. But if you do want rectangular form, remember that just means evaluate your trig functions and then just simplify with distribution. Okay, so there's an example with multiplication. Now let's look at an example where we want to divide two complex numbers. So our division formula says we're going to divide the moduli and then subtract the arguments in the specific order given by the division. So numerator corresponds to the first value, and then denominator corresponds to the second value. Now here our angles are given in degrees. Not a big deal, but we just need to make sure that at the very end, the angle we report for our answer is between 0 and 360 degrees. So Z1 divided by Z2, okay, we're going to take our first modulus, which is 4, divided by our second modulus, which is 12. So notice that's going to remain fractional. That's not going to simplify down to a whole number. That's okay. So we then have the cosine of the difference between our angles, so 15 degrees minus 285 degrees, plus I times the sine of 15 degrees minus 285 degrees. So let's clean all of that up. So 4 divided by 12, that simplifies to 1/3. Now 15 minus 285, let's verify what that is. 15 minus 285, that's going to be negative 270. Okay, that's a problem, right? Because we want angles specifically in the interval from 0 to 360 degrees. So let's go out to the side and let's work with that a little bit. So 15 degrees minus 285 degrees. We know that is equal to negative 270 degrees. So that is a correct argument, but it's not the argument that we want. The preferable argument is going to be the one that's coterminal to that, but between 0 and 360 degrees. So all we would need to do is just find that coterminal angle. In other words, add on 360 degrees. So if we add 360, we get to a coterminal angle of 90 degrees. So even though the formula is going to give us the negative 270, we're going to go the extra step to get that coterminal angle because it's within the interval we want. So that is now going to be the argument. So we have 1/3 times the cosine of 90 degrees minus I times the sine of 90 degrees. And just for the sake, again, of the practice, let's rewrite that in rectangular form as well. Now this one's going to end up kind of interesting because we ended up with something that corresponds to an axis in terms of the angle. So what does that mean for the actual polar number when we convert it to rectangular form? Well, start it out the way we normally do. So cosine of 90 degrees. Well, at 90 degrees, the cosine is 0. And then at 90 degrees, the sine is 1. So the real part is 1/3 times 0, which is 0. Okay? And the imaginary part, well, we have subtraction here. Okay? So, oh, I'm sorry, that shouldn't be subtraction. Let's change that back to an addition. Apologies. Let's fix that. Addition. Okay? Better. So 1/3 times I times 1. So that's going to be plus 1/3 I. And of course, we don't write a plus 0. That's not considered standard practice. So it'll just be 1/3 I. So it is what we, again, refer to as a purely imaginary number. The complex real part is 0, and the imaginary part is 1/3. So even though the original numbers were true complex numbers, they had both a real part and a complex part, an imaginary part, the division, the quotient that results when we divide Z1 divided by Z2 results in a purely imaginary number. And that just has to do with how these angles related to one another. Okay. So we've done a multiplication, we've done a division, we've also converted both of those answers back to rectangular form. So now let's talk about exponentiation. So what if we have a complex number and we want to take a power? Now we're going to assume the power is just a positive integer, so 1, 2, 3, 4, those kinds of numbers. If that's the case, then our complex number raised to this power is given in the following form. We're going to take the modulus and raise it to that power, and then the argument is going to be multiplied by the power. So it's going to be the cosine of n times theta plus I times the sine of n times theta. So that will be the complex form for the exponentiated complex number. Now this is really nothing special in the sense that technically it's just what would happen if we used the product rule a couple of times. So if you were to multiply something by itself, so suppose you wanted to take a complex number and square it, multiply it by itself. Well, you would just multiply the modulus by itself, which would be r squared, hence r raised to a power, and you would just add the argument to itself, which would be 2 times theta, hence n times theta. So this is really just, a specific situation where we would use the product rule, but we're multiplying a complex number by itself rather than multiplying two different complex numbers. Okay, so let's wrap it up with an example using this particular formula. And we'll do it start to finish. So we have a complex number given in rectangular form, and we want the result in rectangular form. Okay, so we're going to have to essentially do every single step here. In order to use the formula, we have to put this in polar form first. Now, technically, this is just a binomial. We're just raising a binomial to the 6th power. It's not technically a binomial, but structurally it looks like a binomial, right? So we would just be raising this to the 6th power. Now, technically speaking, you could do that by hand, but it is not advisable by any stretch of the imagination because of that high exponent. Now, squaring wouldn't be too bad, but if you're raising this to the 6th power, that's like multiplying a binomial by itself 6 times, which you don't want to have to do. Doing that by hand is not something manageable to do. So even though it takes a little time to convert this to polar form and then use the formula and convert it back, you're less likely to make a mistake doing it that way than you are just trying to plug this in and simplify it using standard exponentiation rules. So let's start with the conversion to polar form. So our complex number is -3 plus 3i. If we want polar form, first thing we need is our modulus. So we're going to take the square root of -3 squared plus +3 squared. So -3 squared is 9, 3 squared is also 9, so we're taking the square root of 18. Now 18 is not a perfect square, but it is divisible by 9, which is, so we take the square root of 9 and that gives us 3, and we're left over with the 2. So that is going to be our modulus. Now we also need our argument, so we know that the tangent of our argument of theta is equal to the vertical part, in this case the imaginary part, divided by the horizontal part, the real part. So we get -1. Now -1, again, we've encountered this before. This is something we see on the unit circle, so we can determine theta just by knowing what we know about the unit circle. Now, that being said, remember there's 2 angles from 0 to 360 that have a tangent of -1. Which one do we want? Well, that's going to be based on the quadrant that this particular number is in. If the real part is negative and the imaginary part is positive, then we're talking about something that's in the 2nd quadrant. So the angle we want is going to be an angle that would take us from the positive real axis to the 2nd quadrant. So what angle in the 2nd quadrant would have a tangent of -1? Well, it's going to be the angle 3 pi over 4. So that will be our argument in this case. Now we can take a moment to actually write out the polar form, but we don't really have to, because all we need are these values to then plug in to that exponentiation formula. So we want to take our complex number and raise it to the 6th power. So we know that's going to take our modulus and raise it to the 6th power. So this is going to be 3 times the square root of 2 raised to the 6th power. And then we're going to take our argument and multiply it by 6. So 6 times 3 pi over 4 in both of our trig functions. Okay, and so now we just need to simplify all of that down. Now let's work with the radical first. This is a little bit different. We're not just squaring or cubing, we're raising something to the 6th power. And we also have both a rational and an irrational part. So it's going to be important to focus on those individually. So rather than simplifying everything, let's just focus on that. So that's going to be 3 to the 6th power, and then the square root of 2 to the 6th power. Well, 3 to the 6th power, let's see what that is. So 3 raised to the 6th power is going to give us 729. Now what about the square root of 2 raised to a 6th power? Here's a strategy for dealing with that. Technically, you could put that in your calculator if you want, but if it's something other than 6, specifically if it's something other than an even exponent, you're going to run into problems like that if you put it in the calculator. So here's the way to think of it. Something like an exponent of 6, you could think of 6 like a 2 times a 3. So another way to think of the square root of 2 to the 6th power is in the following way. We could think of it as the square root of 2 squared, and then we could cube the result of that. So essentially I took 6 and I split it up into a 2 and 3 using the power rule for exponents. So the benefit of doing that is we now have a square root squared, which we know will rationalize. And then we can take that rational number and raise it to the 3rd power. So the square root of 2 squared is just going to be 2. And then we're going to take 2 and raise it to the 3rd power, which is going to give us 8. So this is going to be 729 times 8. So 8 times 729 gives us 5,832. Okay, so that's going to be our modulus. Now what about the argument? Let's work with that a little bit as well. So we have 6 times 3 pi over 4. Okay, so 6 and 4 have a common factor of 2. So that's going to reduce to 3 and 2. And that's going to give us 9 pi over 2. Okay, well that's kind of a problem because remember, we want an angle between 0 and 2 pi, and that's larger than 2 pi. So we need to find the coterminal angle that's between 0 and 2 pi. So we want to subtract multiples of 2 pi until we get to something that's within the interval we want. So subtracting 2 pi, say we just subtracted 2 pi once. Well, we would need to get the common denominator, of course. So 9 pi over 2 minus 4 pi over 2 would take us to 5 pi over 2. Now that's still a little bit too big. That's still beyond the interval we want. So I'm going to subtract again. So 5 pi over 2 minus 2 pi, or go ahead and get the common denominator, minus 4 pi over 2, is going to give us pi over 2. And that is within the interval that we want. So this is going to be our modulus, and this is going to be our direction angle. So z to the 6th, after all of that, z to the 6th is going to have a modulus of 5,832, and then our argument is going to be pi over 2. So the cosine of pi over 2 plus I times the sine of pi over 2. And that is our answer. But what did we want? We want rectangular form. So we do want to convert that. We do want to take the extra step we need to convert that. So simplify the trig functions, evaluate cosine of pi over 2 and sine of pi over 2. So that's going to be 5,832 times the cosine of pi over 2, which is 0, plus I times the sine of pi over 2, which is 1. And so we actually have a similar situation to what we saw a moment ago with the previous example. The real part goes to 0, and so we have a purely imaginary number. So 5,832 and our I. So that will be our final answer. If we want to go back to rectangular form, that is going to be our final answer. So again, just to summarize, no real new formulas, just honestly a different relabeling of the same polar and rectangular conversion formulas we saw before. But the benefit of taking a moment and taking that complex number, converting it to this particular kind of polar form, is that we save time in the long run when we want to perform multiplication, division, and exponentiation.